Right now, as you watch this, the moon is sitting about 238,000 miles away, close enough to raise our tides, still gently pulling our oceans back and forth every single day, but far enough away that it's never really threatened us. It's been our only moon for as long as humans have existed. But what if that changed? What if it wasn't alone up there anymore? What if, one day, we looked up into the night sky and saw not one moon, but two, hanging side by side above us? This isn't science fiction. Multiple moons are actually common across our solar system, and Earth almost had one of its own. Here's what that would really look like. This isn't pure fantasy. Mars already has two moons orbiting it right now, Phobos and Deimos. They're small, lumpy, more like captured asteroids than proper moons, but they prove multi-moon systems aren't some rare cosmic exception. Phobos is the larger of the two, heavily cratered, tumbling through a low, decaying orbit that's actually bringing it closer to Mars every single year. Deimos, on the other hand, is smaller, smoother, and sits much farther out, slowly drifting away instead of in. Side by side, they look nothing alike. Different sizes, different shapes, different behaviors, orbiting the same planet at the same time. And Mars isn't unique. Jupiter has dozens of moons. Saturn has more than 140. Even Uranus and Neptune are surrounded by multiple orbiting bodies. Earth, with just one moon, is actually the exception in our solar system, not the rule. So the real question isn't whether a second moon is scientifically possible, it clearly is. The real question is, what would it actually take for Earth to capture one, and what would happen to us if it did? The most likely way it happens is capture. Somewhere out past our orbit, a wandering asteroid, or maybe a small dwarf planet, drifts too close to Earth's gravity well. Instead of slingshotting past us and continuing into deep space, it gets caught, gravity bending its path, pulling it inward instead of letting it go. At first, it doesn't look like much. Just a dark, tumbling rock, dragging a thin trail of debris behind it as it's pulled closer and closer. Over time, its wild, stretched-out path starts to tighten. Earth's gravity slowly reshapes its orbit, pulling it into something more stable, more circular, not a clean, perfect path like our original moon, but an orbit all the same. This isn't instant. It could take centuries. But eventually, that wandering rock stops wandering. It settles in, right alongside the moon we've always known. And Earth, for the first time in its history, has company in the night sky. So let's say it happens. The night sky changes overnight, not one moon anymore, but two, sitting together above the horizon, each casting its own light across the water below. For a while, it would be breathtaking. Two moons rising and setting on their own separate schedules, sometimes close together, sometimes on opposite sides of the sky, painting the ocean with overlapping streaks of silver and pale gold. Coastal nights would never look the same again. People would build entire calendars around double moonrises. Poets and artists would have a new muse. Astronomers would finally have a second, nearby world to study up close. For a moment, this new Earth would feel like a gift, a strange, beautiful upgrade to the sky we've always known. But gravity doesn't care about beauty, and beneath that stunning new view, something else would already be quietly beginning to shift. Tides are controlled by gravity, and a second moon means a second gravitational pull working on Earth's oceans. Coastal cities built around centuries of predictable tide charts would suddenly be dealing with surges nobody planned for. Higher highs, lower lows, and far less predictability than we've ever known. Depending on where the two moons sit relative to each other, their poles could stack together, dragging tides far beyond their normal reach, flooding low-lying streets and harbors that have never seen water rise that high. Or their poles could partially cancel out, leaving tides strangely flat and sluggish for days at a time. Either way, the rhythm we've built our coastlines around for thousands of years would break. Seawalls designed for one predictable cycle would suddenly face two competing forces working against them, sometimes in sync, sometimes fighting each other entirely, and engineers who spent careers calculating flood defenses around a single, reliable tidal rhythm would be starting from scratch. Entire industries that depend on tide predictability, shipping schedules, fishing routes, coastal agriculture, would need to be rebuilt around a system that no longer follows one clean pattern. Estuaries and river mouths would see surges pushing saltwater further inland than engineers ever accounted for, threatening freshwater supplies in ways that had never been part of the original planning. Marine ecosystems, too, evolved around the steady rhythm of a single lunar cycle. Tidal pools, spawning patterns, migration timing, all of it calibrated to a predictability that a second moon would erase almost overnight, forcing entire species to adapt or disappear within a handful of generations. And this wouldn't be a one-time event, it would be the new normal, every single day, for as long as both moons remained in the sky. But the bigger problem isn't the water, it's the orbits themselves. Two moons pulling on Earth also means two moons pulling on each other, locked in a constant three-way tug of war that never fully settles. Orbits that look stable on day one can slowly drift over centuries, nudge just slightly out of alignment every time the two moons pass close to one another. And once that drift starts, it doesn't correct itself, it compounds. If the smaller of the two moons happens to be on the losing end of that gravitational tug, its orbit doesn't just wobble. It shrinks, pass after pass, year after year, pulling it closer and closer to Earth. What starts as an almost imperceptible shift becomes an unstoppable slide, and there's a very real limit to how close a moon can get before Earth's gravity stops just pulling it in, and starts tearing it apart. That limit is called the Roche limit, the distance at which Earth's gravity pulls so much harder on the near side of a moon than the far side that the moon simply can't hold itself together anymore. Once the smaller moon crosses that line, the breakup doesn't happen instantly, but it also doesn't take long. Cracks spread across its surface first, then entire slabs begin separating, drifting slowly away from what's left of the core. Within a relatively short window, astronomically speaking, that moon stops being a moon at all. It becomes a widening field of rock and dust, still following the same orbital path it always had, just no longer held together as a single body. And because all of that debris is still moving at orbital speed, it doesn't fall, it spreads out, stretching into a long, thin arc that begins wrapping itself around the entire planet. Given enough time, that arc of debris settles into something we've only ever seen around Saturn or Jupiter, a ring. Not a thick, dramatic band like Saturn's, but a thin, faint one, made of ice, dust, and rock fragments left over from a moon that no longer exists. Earth, once a single moon planet, would end up with one moon remaining and a delicate ring circling its equator, catching sunlight at just the right angle to glow faintly at dawn and dusk. From the ground, it might look like a strange, pale band stretching across part of the sky, subtle, easy to miss during the day, but unmistakable at twilight, when the low angle of sunlight catches every particle drifting along its length. Over centuries, that ring wouldn't stay static either. Gravity would keep working on it the same way it worked on the moon that created it, slowly pulling some of the debris further out, letting some of it drift inward, until parts of the ring began raining down as a faint, ongoing meteor shower, visible from the surface for generations. Future astronomers looking up at that sky wouldn't just see a ring. They'd be watching the last physical remains of a moon still falling to Earth, one tiny fragment at a time, centuries after the moon itself had stopped existing. It would be a permanent reminder, written into Earth's own sky, of a second moon that came, disrupted everything, and ultimately didn't survive the encounter. So the two-moon Earth doesn't end in some stable double-moon paradise. It ends as a slow, centuries-long process, one that reshapes our tides, destabilizes our orbits, and ultimately leaves us with rings of our own. All from one extra moon showing up in our sky. If you want to know what it actually feels like to fall into a black hole, and what happens in the seconds before you cross the point of no return, hit subscribe. That's exactly what we're covering next.